In the landscape of modern astrophysics, the title of most dangerous planet is no longer a work of fiction. As of 2026, we characterize these hostile worlds through precise thermodynamic limits. WASP 76b has emerged as a primary candidate for this distinction. It represents a world defined not by chance, but by the relentless physics of extreme heat, crushing pressure, and chemical volatility. By studying these extreme environments, we push our understanding of atmospheric physics to the absolute limit. Meet WASP 76b, an extreme world classified as an ultra-hot Jupiter. Its orbit brings it so close to its parent star that the entire planet is scorched by intense radiation. Due to the immense gravitational influence of its star, WASP 76b is tidally locked. Just as the Moon faces Earth, one side of this planet faces its star eternally, while the other remains in permanent frozen darkness. This creates a massive temperature imbalance. The day side is baked in constant, searing light, while the night side provides a sharp contrast. This thermodynamic divide drives the planet's chaotic atmospheric weather. On ultra-hot gas giants, temperatures on the day side soar beyond 20,400 degrees Celsius. This heat is so extreme that it vaporizes solid metals. These metal gases are pushed by powerful jets to the cooler night side. There, the sudden drop in temperature causes the iron gas to condense into liquid droplets. This cycle creates a literal, permanent rainfall of molten iron. It is one of the most violent weather systems ever observed in our galaxy. Atmospheric superrotation is a phenomenon driven by extreme stellar heating. On these planets, the atmosphere absorbs so much energy that winds circulate faster than the planet rotates on its axis. This thermal imbalance generates massive convective loops. These loops force the atmosphere into a state where it orbits the planet in a continuous, high-velocity stream. While we see examples of superrotation in our solar system on Venus and Titan, on ultra-hot exoplanets, these winds reach supersonic speeds. These winds do not dissipate. They form permanent, planet-wide storm systems that churn constantly, redistributing heat from the day side to the night side. Tidal dissipation is a brutal process driven by the host star's immense gravity. When a planet orbits in an eccentric path, the star's gravitational pull constantly stretches and squeezes it. This gravitational conflict is best observed through orbital eccentricity. As the planet gets closer and further from the star, tidal bulges fluctuate, converting orbital energy into internal friction. Deep inside, this friction transforms the planet's interior into a superheated, molten nightmare. The asthenosphere is constantly melted by this internal churn, leading to extreme volcanic activity. Essentially, tidal dissipation turns the planet itself into a giant heat engine, ensuring that the world remains geologically volatile and inhospitable. HD 189733b is a gas giant exoplanet that orbits its star with extreme intensity. It is famous for weather patterns unlike anything in our solar system. The atmosphere on this planet features supersonic winds reaching 5,000 miles per hour. These winds circulate around the planet's atmosphere at a constant, blistering speed. The atmosphere contains silicate particles that condense into solid form. Driven by these ferocious winds, they become sharp shards of glass that fall horizontally across the planet, creating a lethal, horizontal rain. This alien environment remains a profound subject of study in exometeorology. Exoplanetary weather is driven by extreme phase changes. Let's compare two of the most hostile worlds we know. WASP 76b faces temperatures hot enough to vaporize iron. On its night side, that iron condenses and falls as molten rain. In contrast, HD 189733b features silicate clouds. These particles condense into glass, which is then swept across the atmosphere by supersonic winds, creating shards of horizontal glass rain. While the materials differ, iron versus glass, both represent phase transitions occurring under extreme conditions, defining the chaotic meteorology of these worlds. Deep in the Cancer constellation lies 55 Cancri E, an exotic super-Earth. This world is a nightmare of extreme heat. Its entire surface is likely a deep, boiling ocean of liquid magma. Temperatures here are high enough to vaporize solid rock. The planet is so close to its star that the surface remains in a constant state of flux. By studying 55 Cancri E, scientists gain critical insights into how planetary surfaces behave under extreme thermodynamic limits. Kepler 70b is a world that defies the odds. It is one of the hottest known planets in the universe, having survived a cataclysmic transformation of its host star. When its host star expanded into a red giant, the planet was almost engulfed. It narrowly escaped, resulting in an orbit so close that the planet is now subjected to extreme temperatures. The surface temperature of Kepler 70b actually exceeds the surface temperature of our own Sun. It sits incredibly close to its remnant star, a hot B subdwarf. At these temperatures, the planet is not just hot, it is essentially a scorched remnant of its former self, providing scientists a unique look at how planets interact with the violent end stages of stellar evolution. In the study of exoplanets, there exists a critical threshold known as the threshold of hell, 1,500 degrees Celsius. Above this temperature, the atoms within a planet's atmosphere become so energetic that electrons are stripped away, transitioning the gas into plasma. This ionization process blurs the boundary between a gas giant and a star-like object, creating a transition where the planet behaves more like a captive solar furnace. High-energy radiation from host stars, specifically X-rays and ultraviolet light, drives a process called atmospheric erosion. This stellar bombardment strips away the outer layers of a planet's atmosphere. As the planet absorbs this intense energy, atmospheric gases heat up rapidly. This causes molecules to reach escape velocity, effectively boiling off the atmosphere into the vacuum of space. Radiation creates distinct physical changes. X-rays are more efficient at heating because they can penetrate deep, while FUV radiation primarily influences the outer valence shells. The James Webb Space Telescope is our premier tool for decoding the atmospheres of hostile exoplanets. It acts as a powerful chemical detective, capable of capturing the faint light filtered through distant alien skies. At the heart of this mission is the NIRSPEC instrument. It breaks incoming starlight into its component wavelengths, creating a detailed spectrum that serves as a unique chemical fingerprint. By analyzing these spectra, we identify specific absorption lines. Each molecule, like water, methane, or carbon dioxide, leaves a distinct signature in the light data, revealing the composition of worlds light years away. This instrumentation allows us to push the boundaries of what is observable, turning distant, hostile environments into accessible laboratories for extreme planetary science. To study extreme exoplanets, we use spectroscopy. This technique analyzes the light from stars that filters through a planet's atmosphere to reveal its chemical composition. When light interacts with gas, it leaves a unique fingerprint. By studying how gas absorbs or emits specific wavelengths, we can identify elements like gaseous iron or silicates. A prism or diffraction grating spreads light into its component colors. By isolating specific beams, we can measure how much light is blocked by the planet's atmosphere. This graph shows the stellar flux. The sharp dips you see are absorption lines, acting as a chemical barcode. Each dip confirms the presence of specific elements, showing us the hostile chemistry of these worlds. Through chemical fingerprinting, we transform distant, invisible worlds into detailed data, uncovering the extreme physics of the universe. Why investigate worlds where lead melts and iron reigns? These planets act as extreme laboratories, pushing the physics of atmospheres to their absolute limits. By studying these extremes, scientists can refine the climate models we use here on Earth. When a model works for a hellish exoplanet, it gains credibility for Earth. Observing different atmospheric compositions helps us understand how a planet's chemistry dictates its ultimate fate, from life-supporting to scorched. Ultimately, these hostile worlds are the stress tests that help us understand the fragility and stability of our own environment. Exometeorology is the emerging field of study dedicated to mapping the weather patterns of planets outside our solar system. We are moving beyond simple detection, where we only confirm a planet exists. Instead, we now use high-resolution spectroscopy to analyze atmospheric dynamics, tracking winds, temperatures, and cloud formations in real time. This allows us to see how extreme energy drives global storms and temperature shifts across these hostile yet fascinating cosmic laboratories. Recent data from the ESA Gaia mission has transformed our understanding of the galaxy. It reveals that extreme, hostile planetary conditions are far from rare anomalies. Our findings indicate that 15 to 20% of gas giants orbiting close to their host stars exhibit these dangerous atmospheric characteristics. This suggests that these hellish worlds are a common occurrence in our galaxy, not just cosmic flukes. Looking ahead to the 2030s, the Habitable Worlds Observatory will represent our most significant leap in exoplanet research. Its primary mission is to identify rocky Earth analogs. We are specifically searching for planets with aggressive, Venus-like greenhouse effects. By analyzing these atmospheres, the observatory will help us understand why some planets evolve into temperate worlds like Earth, while others become hellish, high-pressure ovens. This future technology will provide the data necessary to redefine our understanding of planetary habitability and the absolute limits of atmospheric survival. The classification of extreme exoplanets challenges our definitions. When a planet reaches temperatures comparable to a star, at what point does it cease to be a planet? We often look to brown dwarfs or failed stars. These objects exist in a transitional state between massive gas giants and true stars. The Hertzsprung-Russell diagram maps these objects by luminosity and temperature. Planets and brown dwarfs occupy the lower, cooler regions, distinct from the main sequence of burning stars. At surface temperatures exceeding 1,500 degrees Celsius, the atmosphere transitions from a gas to a plasma. At this point, the physical distinction between a planet and a star becomes thermodynamically blurred. Defining these worlds isn't just about labels, it's about understanding the extreme limits of matter and energy in the universe. The environmental conditions on these extreme exoplanets present an insurmountable survival constraint. No known material created by humanity can withstand the forces present on these worlds. A human would be incinerated instantly by temperatures exceeding 2,400 degrees Celsius. The extreme atmospheric pressure would crush any vessel, while supersonic winds would shred all known structural materials. In short, these environments represent a lethal boundary. Whether by heat, pressure, or kinetic impact, they remain entirely hostile to any form of conventional technology or biology. For decades, our understanding of planets was limited, often viewing them as static, geological rocks sitting idle in space. Modern science has sparked a paradigm shift. We no longer see these worlds as frozen in time, but as complex, chaotic, and fluid systems. Using data from powerful telescopes, we now recognize planets as fluid-driven engines, defined by constant atmospheric exchange and internal turbulence. When we label a planet as the most dangerous in the universe, we are using a human-centric definition. Danger is relative. To life as we know it, these environments are lethal. But to an astrophysicist, these extreme worlds are not dangers. They are invaluable laboratories. By studying these hostile conditions, we push our models of physics to their absolute limits. They provide the extreme data points required to understand the universe's mechanics. So, while they may be hellish to us, they remain the most important treasures of knowledge in our search for cosmic truth. We have examined the extreme environments that classify exoplanets as dangerous. Let us synthesize these threats into three distinct categories. Thermal destruction occurs when extreme stellar proximity vaporizes rock and metal. Simultaneously, high-energy radiation triggers mass loss, stripping the planet's atmosphere into space. Physical erosion stems from supersonic winds and debris like silicate shards. These forces act as a constant, abrasive blast that reshapes the surface of these hostile worlds. By combining thermal limits, physical erosion, and atmospheric erosion, we map the absolute limits of planetary survival. These worlds are not just chaotic, they are extreme laboratories for atmospheric physics. As we conclude our journey, we realize that the title of the most dangerous planet is a shifting target. It is redefined not just by the harsh realities of space, but by the sensitivity of our own tools. By studying these hostile extreme environments, we are actually learning how to define stability. We push the limits of physics to better understand why Earth is the fragile, unique haven that it is. Every hostile world we uncover serves as a landmark on our map of the cosmos. Our search for these extremes is, in reality, our quest to find our own place in the grand unfolding story of the universe.